Hello and welcome. We are finishing off this whole course, I suppose, right now with an analysis of QuickSort. So we're going to visit sorting one last time here, and we are going to discuss QuickSort, which is the sort we had previously sort of alluded to as another divide and conquer sorting algorithm, but we hadn't actually done anything with it. So let's take a look at it right now. So basically, by the end of this video, you can expect to understand how QuickSort works, both conceptually and also be able to follow the code and understand the Java code. It's going to work very similarly to merge sort, with the idea being like how we do our recursive calls. So if you feel good about merge sort and like sort of visualizing the runtime stack, this won't be a big leap for you. If that's still a little bit of a struggle for you, I do recommend that you go back and re-review the merge sort video, because I do go into a lot more depth in, I think it's 7.2 is the merge sort video, where I go into like deep depth of that runtime stack and what the calls look like and stuff like that. So if you need a refresher or some more time to sort of process and digest that information, I would recommend going back to watch that before watching this one. We're going to learn about how the pivot choice as part of the algorithm, that is the QuickSort algorithm, affects running time, because the running time is actually very tightly coupled with the choice made when you are running when you're running through this algorithm. And then we'll also be able to connect the idea of a good versus a bad pivot when we're talking about this idea of overall efficiency in sorting. So let's just very quickly remind ourselves that insertion sort is a bit like shelving books in a library, where you have your set of library books and they're all out of order. And so you sort of just take each one and put it in the right order, sort of shoving over the ones that are still need to be sorted. So imagine if you have your library shelf, and each of these represents a book to be sorted. And we start with this book and we say, okay, let's sort it. We put it there. We take this book, we sort it there. We take this book and we know it has to go right between these two. So we shove this book over and it gets sorted right there. We take this one and we realize it has to go at the front. So all these books get shifted over a little bit so that there's space for this one, and perhaps this one goes here. And now we have a nice sorted set of books done through ordered insertions. Next is the selection sort, and the selection sort is kind of like when you are drafting basketball players, like for your team or whatever. So first you pick, your top pick, and then your second pick, and your third pick. And as you're building out your team of basketball players, the pool of players unsorted players gets smaller, and the pool of desired players that you've selected in the order of which you've selected them continues to grow. And then, of course, we did merge sort most recently, which is a bit like organizing puzzle pieces by sections. I'm such a big jigsaw puzzle person, so like this makes perfect sense to me. But like when you start with your puzzle, you have like a jumble of pieces. These are my really nice puzzle pieces, right? And they're all like jumbled together. And so like, what are you going to do? The first thing you might do is you sort them first by color. So you end up dividing them out like this. Whoops. And then after you've done that, perhaps within here, there's like different types of blues or different types of reds or different types of greens, right? So first we went with all the greens in one place. We did all the blues in one place. We did the pinky reds in one place. And we sort of just keep dividing until we end up with piles that we can actually start to work with until it becomes manageable. Oh, go back over there. Right. And so we can see how it's a merge sort might be a bit like sorting puzzle pieces, because once you've sorted it down to like a manageable set of puzzle pieces, you can start recombining it into like an actual like shape. Probably this would end up actually all being like the sky, and then like, whoa, those fit together so beautifully. You've got your like grass going on down here. So it's gonna be a really nice puzzle, as we can definitely all tell. This is so funny. What a ridiculous concept this is, but that's okay. I'm here for it. And then, we grab these pieces over here, and for one reason or another, we realize, oh, these are ducks in the ground, on the ground, or a person or whatever. And we end up with our full puzzle once we've recombined it all, right? I got way too into that analogy. I'm so sorry. Okay, so those are our three sorts that we've already looked at. So now let's look at QuickSort. And of course, it wouldn't be one of my videos without there being some kind of ridiculous analogy. So get ready for sorting your closet. So let's say that we have our closet and of clothing, and we really want to make sure that the items that we like love to wear a lot are the easiest to access because we wear them like every day or whatever. And the clothing that's maybe like we don't like it as much, or it's only for special occasions, or really whatever sorting criteria, your favorite to least favorite means to you. You just want to sort of be able to put those in that order. So how are we going to do this? Well, we start by just like picking up an item, and we're going to sort all of our clothes into two piles, the ones that we like less than that item, and then the ones that we like as much or more than that individual item. And then once you've done that, you're going to do it again. So imagine for a second, you've got a shirt that, oh, really, that was not a shirt. A shirt here that is our starting item. And I say, I like this skirt less. I like this skirt more. I like this shirt less. I like this shirt more, whatever it might be. I like this long sleeve shirt more. I don't know. There we go. Don't judge my drawings. But basically, we end up with two piles that like these decisions have been made around our original chosen shirt. So then we do it again. So now we're going to go into this pile here, and we'll like pick one and then decide for every other item if we like it more or less than that item. And then we'll pick one and decide if we like it more or less than that item. And we sort of just keep recursively making our problem space smaller, right? We're dividing our problem space down and down until we hit a pile that can't be divided any further. So if we imagine taking this pile, we took this item and said, well, we like this shirt more. Now we're going to go into this pile. Oh, it's empty. We go into this pile. Oh, there's only one thing. We can't divide that any further. We've hit piles here that cannot be further divided. So now we start our conquer step, right? Divide and conquer. We recombine everything in the reverse order. So starting with the very last pile that you touched, you're going to start recombining your clothes. I actually want to change this. This is obnoxious of me, but I probably want to put my most liked items in front. So I probably do most liked first, then my favorite item, then my least liked items. Just flip those two words there. Okay. So let's actually do this visually. So here is a cute kid, and they want to organize their closet. We can see all the items in their closet above their head, and they are ready to do this. I wish my children would sort their own closets. So the very first thing that the kid does, they say, let me grab my first shirt that I can reach. So they just go ahead and they just grab this first shirt that they can reach, and this becomes their anchoring shirt. I say anchoring because it's like anchoring bias, where it's like, now that we've picked this one, we're just making choices that are relative to the first shirt that we picked. And just like anchoring bias, there's bias in that, right? If we picked our favorite shirt of all time, everything else is going to end up being less liked. If we picked our least favorite shirt of all time, everything else is going to end up being a favorite. And kind of what we hope for is an average case where like, we like this shirt, but it's not really one extreme or the other. We just grab the first shirt that we can reach. And now that we have it, we're going to ask ourselves, for each other shirt, do we like it more or less than this anchoring shirt? So I look at this one and I say, if I like it, less, I'm going to put it here. But if I like it more, I'm going to put it over here. And I do that for every single one of the shirts in my closet. So we come down here and we see that our little helper is done. Here is the shirt they started with as their anchor shirt. Here are the shirts that they decided that they liked more, and here are the shirts that they decided that they liked less. So now they're going to follow that steps that we just laid out up here, which was most liked, then that anchoring, then less liked. This is very similar to how we would do right side of our array and merge sort, or sorry, left side of our array and merge sort, and then the right side of our array in merge sort. The difference being we can't forget we have like this middle shirt here that has to eventually also be processed. But we're still going to try to do left to right. And in this case, we're putting the easiest to reach. So our favorite shirts on the left and then our least favorite shirts on the right. Okay, so we go one step down and we do it again. We're going to look at each pile. Once again, we're going to do the likes more first. We're going to start with the things we like more. We pick a shirt. This one's closer to our little helper friend here. So they grab this shirt, plops it right in the middle. And then for every other shirt in this sub pile, they decide, do I like this shirt more or less? There's only one other shirt and they decide they like it more than this shirt here. So then they're done and they are going to do this again. They're going to go looking in this pile over here and they're going to say, hey, there's only one shirt in there. There's no more sorting to do. So then they come back and look at the less pile and say, well, the less pile is empty. So there's no more sorting to do there either. So since there's no sorting here and there's no sorting here, it's time to start recombining. So they're going to go ahead and recombine this and they recombine by likes more, by our anchor, and then likes less. And so we can see that right here. Likes more arrow goes back at the front, our anchor, and then likes less. And of course, there is nothing in likes less, but in theory, it would go there. Okay, once we've done that, there we go. We can see that those have been moved in. Once we have finished that step of like processing likes more, remember we still hadn't touched the likes less side of our original subpile. We come back up to the top of our we've gone pretty deep in these piles of laundry. We come back out of our piles of laundry and we say, okay, well, we finished processing everything on this side of our anchor shirt. We have to go process stuff on this side of our anchor shirt too, if there is anything, right? And there is. But we know that everything to like this side of our dino shirt, we like less. So that means we know our dino shirt is going to go right here. And then we're going to, process our likes less pile. So we come down here. We've put dino shirt right up there, and now it's time for us to process likes less. So we go into our likes less pile, we grab a shirt that we can reach, first shirt we can reach, it becomes our anchor shirt. And then for every other shirt in there, we once again go ahead and look through and decide which one we like less, which ones we like more, etc. Once we finish processing it, we go into the likes more pile and we realize this is sorted already. There's only one shirt in here. So then we come back up and we go, likes less pile. Oh, this is already sorted as well. There's only one shirt in there. So since there's no more sorting to do, it's time to do our recombining from this level. Our likes more goes in first, then our likes less, then our anchor shirt, then our likes less. And we actually end up coming back up to our original set of laundry piles. We say, let's go check for the next pile. But there was no piles left. We've already finished sorting all of our piles. So my closet is sorted from my favorite shirt all the way down to my least favorite shirt, with that anchoring shirt, falling wherever it falls in that ordering. So that's our quick sort, how we do it. So what are some of the big facts for this process? So, when I think about solving mathematical proofs and stuff like that, I often will write out this idea of big facts. So like, what are things that we just know to be true in order for us to kind of develop a better understanding of this algorithm? Well, we understand that if a pile is empty or has one element, it can't be further divided. We know that this is true from merge sort, and we also know it's true here. We saw it happen. We also know that we always processed our shirts in the order of divide around a given shirt, then go check out our favorites pile, then we moved our anchor shirt into our closet, then we checked out our less favorites pile, right? That was kind of the order in which we did things when we were doing our combining. So we went all the way down. This divide was kind of like divide faves, divide uglies. I don't know. I hope they're not uglies, but the other ones. And we just kept doing that. So we kept dividing all of our faves until there was no more faves to divide, at which point we would move favorite in, then anchor, then least favorite of the favorites. Then we'd go up a layer and we would divide the uglies, and we would do the same thing. And again, if you remember the merge sort video, this is exactly like what happens in merge sort. I showed at the end of the merge sort video truly just how the order of like the operations goes, like the actual flow of execution isn't top to bottom, left to right, but it was more of like a wavy pattern of like all the way down this way in the tree and like this. And we did it with different colored arrows. And like, it's the same idea here, where the first thing we do is we process our most favorited shirts. And then the very last pile that we ended up processing was our least favorite shirts. And then we can start combining things back up. So we can see that if a pile is empty, it has, one element and it can't be further subdivided. This is our base case. 0 shirts or 1 anchor shirt, and that's it. There's no work to be done here. There's no, comparisons to be made. That's our base case. Whereas in the other situation is our recursive case. We separated our shirts into favorites, which were on the left of our array in the end, and our less favorites on the right, our uglies, as I so beautifully put it. And then we looked at our left pile and we processed it just like we did in merge sort. Once we hit the bottom, we were able to place our anchor shirt in its new home. Once we had favorite, anchor shirt, other shirt, ugly shirt. And then we looked at our right pile and processed that just like merge sort. So here is our code, sort of an example of the code and how it looks. And what we can see here is the way in which this merge sort is done is it is done in place. So in my example with shirts, I was actually dividing the array out at each level. I was basically making new arrays just like you would in merge sorts, because I was showing it to you like as if we had 2 piles of laundry that we were separating on our floor. But in reality, QuickSort is more like binary search, where it's done in place and all we do is alter the low and high boundaries. That's all we have to do. So we just sort of set the range in which we're currently looking at. And that's actually enough for us to figure this out. And just like in binary search, as long as low is less than high, we still have processing to do. And at some point, that's no longer the case. We know that we've hit our base case. And there's nothing to do on our base case, as we just saw, right? Base case, no work to be done here. Okay, so the very first thing we do is we have to partition our array based on that pivot index. That partitioning is the step of picking a pivot value, picking an anchoring shirt, and just dumping the things that are bigger than or smaller than it on either side in our array. Or in our situation, things that we liked more and liked less on either side of our anchoring shirt. Once that step's been completed for a given like low-high boundary level, we can call QuickSort on the left side, and then we can call QuickSort on the right side after. So we can see exactly how that's going to go all the way down. In our partition step, it's exactly kind of as we'd expect it to be. Now in this code, you'll see that they chose the last element to be the pivot, whereas in my clothing example, I chose the first element to be the pivot. And we're going to talk about pivot choice in a minute, but it's just worth noticing that they did make a different choice than I did in my example. We can see that they also start I at 1 less than the low boundary, which means that I starts at -1 when low is 0. And that's just really important. We have to notice that. And then we can do our swaps. We do our swap if the current element is less than or equal to pivot. We increase I and we do a swap. And I actually will show this with numbers in just a minute. So we do that all the way through the entire range in our array. And then at the end, we go ahead, we swap our pivot value, which was at array high. So we swap our pivot value into the middle. So like we give the pivot value a chance to be swapped into the correct spot. And then we can return this this value that of where our pivot actually is now. So that's what this returns. Partition returns where the pivot actually is, which makes sense since back up here it was called pivot index. And then this is just a normal array swap, nothing fancy there. Pardon me. Okay, so let's actually look at this with like an array of numbers just to get a better feel for this here. We're not going to like ask you to rewrite the QuickSort code because I really don't care if you can write QuickSort code because you could literally just copy paste this. But it is important that you understand sort of the nuances of the algorithm. If I asked you to like, we'll get to the discussion questions, but basically the pause and practice is going to be the kinds of questions you might see on an exam. Okay, so just like in my previous example, I'm just going to pick the one closest to me. That's my easiest one, just like my anchoring shirt. And I'm going to swap the pivot to the end, go through my partitioning steps, tracking my partition index, and then I will swap the pivot into the right spot. So we're going to just go through sort of one level of this entire QuickSort process. I'm not going to do the whole thing just because it does involve a lot of iteration, but it should be enough for us to get the basic idea. So we'll see, I do start my I at -1 because my low is 0 right now. And I swap my pivot to the end. So whatever was in the end previously, it was 10. I just did a swap. That's all I did. Straight up, just did that swap to get things started off. Okay, now it's time for me to do my partition steps and tracking index. Okay, I forgot I wasn't using like my laser there. And so it like stuck around. Okay, so first thing we do is we compare ourselves to the very first position here, which I'll just label as index equals, actually that might be confusing because I'm using the word index in other places. I'll just say J, and this is just like our iteration variable in our loop. So we start with J equals 0 and we compare it to our pivot and we see that it is greater than our pivot. So we do nothing. This is because we are going to be sorting these values from small to big. Of course, if it was in the other direction, everything would be reversed. So we do nothing. Amazing. We're already off to a good start. This means that our J can now increase to 1 and we can compare 3 and 7. We see that 3 is less than our pivot value 7. So we do exactly what our code did. Increment I, swap with 10. So we're going to increment I to 0, and we're going to swap it with whatever is there. So let's go ahead and see what that looks like. Right there, we see it, right? So we see that our I did indeed become 0, and we saw 3 and 10 swap places. We went from this, and these two swapped. Current and whatever's in I swapped. So this is like swapping with I after that increment. I wrote 10, but swapping with I. And then we go to the next one, right? So now J is equal to 2. We ask the exact same question. Is this less than or equal to this? And it is. So we're going to increment I and swap with 10. Why are we swapping with 10 again? Well, because we first increment I. So I is going to become 1. And then we're swap with whatever's in I. And it is 10 again. So 1 and 10 are now going to swap places. There we go. I equals 1. So we saw that increase happen and we saw 10 and 1 swap places. Now we see 8 is greater than 7. So we don't do anything. Nice, easy step. Our J can just increment again and we'll go to the next one. Here we see 0 is less than 7. So this is going to be another increment and swap. So again, that means that I is going to become 2. If you're following along, 0, 1, 2, 3, 4, 5. So what does that mean? That means I became 2 and we swapped 0 with whatever was in the position that we needed to swap with. So what I is actually representative of, I feel like I should ask you, like leave that question hanging. What does I represent? I represent, and then like pause and think about it. And then I'm going to answer it and say, I is representative of where the smalls stop and the bigs begin, right? So when we do I++ in this scenario, we end up right here. And because we're doing a swap with 0 and 7, I is literally going to be the last of the small elements. It is the last element of like the subarray that's less than the pivot. So we go ahead and we do that swap. And now we see my iterator index, which is what I've been referring to in this video as J, is pointing at my last element. It's at my pivot, so I stop. I don't have to do anything with my pivot. So at this state in the program, I is 2, which, as we said, is representative of the very last element in the subarray of smalls. These are all less than the pivot. And everything from I+1 to N, or I guess N-1, is going to be bigger than our pivot. And we know that our pivot is in this position right here. So what are we actually going to do now that we've hit this point and we've stopped? Well, once we've done this, we need to swap the pivot also into the right place. Now, right now, I is equal to 2, which means if I swap my pivot with I, we would end up doing something like this. And we can already see that that's not going to work, right? That's going to break our sorting because now there's something smaller than 7 on this side of 7, and that's bad news. So since this element here is our last small element, we just say I plus 1. And so we go from I plus 1, and we swap whatever's in I plus 1 with our pivot right there, and we end up like this. Now we can break our array up into 2 separate pieces. We have from 0 to I being smaller than our pivot. And we have from I to N being, well, I guess this is, yeah, being greater than or equal to our pivot. This is probably actually a little bit inaccurate. Depending on your implementation, this is probably less than or equal. And this one is probably just strictly greater than. But it really depends on your implementation. I just think I said that earlier, that this was going to be the order we'd be working with, but there are no duplicates in here, and really just comes down to consistency and like if you implement it, leaving comments of where these things might go. So now we can see how we could do this again on this subarray. Pick a pivot, do our partition, pick a pivot, do our partition, right? We can see that. We can do it on, on this subarray after. And we can also see now how this kind of translates back into what we originally had, which means, if I pick 3 as my smallest value, those would swap. 0 is less than 3, so we'd do nothing. 1 is less than 3, so we'd do nothing. There's no 3 swaps with itself. We'd now run this on 0 and 1. 0 is our new pivot, so these would swap places, right? We always put our pivot at the end. Oops, I rewrote it the same. There we go. We'd see that 0 is greater than, that 1 is greater than 0. So these would, well, actually, we would not do anything. And then I would need to be moved into, the pivot would need to be moved into its spot at 0 and 1. And then 1 would now be our array, and 1 is already in the right spot. So what happens is we go back up our chain here of moving things. Like, I mean, I guess there is no moving things back because it's an array, but we're not merging 2 sorted arrays. This was all done in place. So what this actually means is that 0 is in the correct position from this run, 1 is in the correct position from this run, and 3 is in the correct position from this run. So we can actually see how at each level, those kind of would find themselves in the right position. 7 doesn't move. 7 is like our anchor shirt at the top level that we know doesn't need to move. And then we would do the exact same thing down the other side. And so we would end up with 0, 1, 3, 7, 8, 10. So it's kind of neat how that works. And as you're sort of trying to understand this, I often find it helps to, like, with each of these steps in the code, actually print things out as you go. So like print out after the partition, like print 0 to the pivot index and the pivot index to N, just so that you can actually see sort of what's happening at each level. I find that pretty helpful. Okay, let's continue here. There is a website here that you can go watch a full visualization. I'll just click it for now so that you can just sort of see what I'm talking about, but we're not going to watch it right now. Here they have, it's called Visual Algo, and you'll see up at the top here, there is like a bunch of different types of sorts: selection, insertion, merge, and then QUI is QuickSort. There's other things here as well, but really what I'm suggesting you watch is the QuickSort one. You can create a random array. You can decide, if there's duplicates or not. You can hard code values into this array, and then you can run it. And there's like a full visualization that you can watch as the pivot is doing its job and as everything is being worked through. You can see, the red one is, I should pause this while I'm speaking. There should be a way to pause it, but I can't remember now. Pause. No idea. Anyway, we can see sort of that the different colors are representative of what we're currently looking at. The yellow is always the pivot. Just notice here that when they pick their pivot, they actually don't move it to the end, they leave it in the front. So their algorithm, like this algorithm, does look a teeny tiny bit different than the one that I just showed you. But that's okay. It's just, worth noting. And why are they doing it differently? Well, we're about to talk about, again, like, let's not lose the thread here, why the pivot choice matters, right? So I picked a pivot situation. This version is picking a pivot situation. Let's take a look and see what decisions we can make that affect this algorithm. Okay. So how bad can a pivot be? Let's imagine for a second, let's just follow suit from before. I choose the first element as my pivot, but suddenly my data is different. Previously, I had like random, pseudo-random data. Now I have ordered data. But let's pretend like I don't know that. And I just pick the first value as my pivot. So what ends up happening is after the first round of partitioning, my left side is empty and my right side just has 2, 3, 4, 5, 6 in it, right? It's all the elements because 1 would have been moved over here. So we would have ended up with 6, 2, 3, 4, 5, 1. And I would have found that 1 is less than 6, so this wouldn't move. 1 is less than 2. 1 is less than 3. 1 is less than 4, and 1 is less than 5. And so we'd end up with my pivot spot of my left being non-existent. This is my less than ones. And then I'd have these all, those are all my greater. I guess this is less than or equal, we said. Got to write things a little bit nicer. Less than or equal, greater than ones. And we can see that we end up kind of unbalanced, right? Like in our previous example, it wasn't perfectly balanced per se, but it wasn't quite so skewed either, of like literally one array being like one subarray is completely empty and one of those subarray partitions is filled with everything. So if our pivot doesn't split the array approximately in half, each element ends up doing n minus 1 comparisons. So instead of getting, I wrote log n, but I meant n log n, right? Like for every element, we had log n comparisons. Instead of getting an n log n, like it should be, like merge sort, we get something else. So I'm just going to write that down. What we want is that like every element 1 to n ends up getting compared with ideally max log n elements. And then we end up with what we hope is an n log n sort, just like merge sort, ideally. But that's not what necessarily happens if we pick a really bad pivot, because like I said, every element ends up doing that n minus 1 comparisons, which means instead we end up with every element 1 to n for each element compare with n minus 1 elements. Instead of saying compare with log n, we're saying compare with n minus 1. And then that's like saying n times n minus 1. And if you remember from the previous videos, we don't care so much about that minus 1. We basically just get rid of it at the end of the day. And we end up with n times n. So this ends up with a runtime of n squared, right? So there's actually a huge difference between n log n and n squared. You're going to learn a lot more about this next year. But just based off of the previous videos, hopefully we understand that these two values are quite different. Our insertion sort and our selection sort are n squared sorting algorithms, and they're not very efficient. And QuickSort is supposed to be better, but with a bad pivot, honestly, we end up greatly affecting our runtime for this algorithm. So what does this mean for us at this point? Try to run through QuickSort yourself. Draw it out, draw each of those iterations as you walk through it, and then you can try to code it up and see if you're right. You can use the visualization tool to help check your answer before you just copy and paste like the code solution to see if it works, which I would recommend, because once you copy and paste the coding tool, like the solution code, it's kind of game over in terms of your learning. Just remember that if you're going to use the visualization, you should follow the same pivot choice that they make, which is picking the first element, but leaving it there. Because while your end answer will end up the same, your intermediate steps might look a little bit different depending on your pivot choice. And if you do less than or equal versus strictly less than, those kind of things can make a difference if there's duplicates and stuff like that. Okay, so then once you've done that, let's just consider the following. And this is really where like some good exam questions come in. If I asked you to pick the pivot, what number would you pick to split the list evenly? And would you pick a better pivot if you knew more about the data set? Knowing that it's a sorted data set or almost sorted data set, we probably want to pick a pivot value that's somewhere in the middle, right? So obviously, if the data set is already sorted, 4, 5, 6, 7, there's nothing to do. But what if I told you that the data set looked something like 1, 7, 6, like almost sorted. Like it's not really sorted yet by any means, but it is almost sorted. And like there might be a better choice here. Actually, I'm going to even switch 5 and 3 here. Picking 5 would only leave 6 and 7 on one side of it and 1, 2, 3, 4 on the other side. And we could get a much more balanced split if I took this middle value instead, right? We would end up with 1, 2, 3 on one side and 5, 6, 7 on the other side. So if you knew that the data was almost sorted, you almost have a better chance of picking a good pivot if you go and you pick that middle value, as opposed to always picking the front value, right? We can see why that might be the case. But what if we don't know anything about our data set? You know, how can we make a smart choice? Lots of research has gone into this. There are lots of different ways of picking a pivot and partitioning data because we don't want to be in the worst case scenario. So lots of researchers have spent time trying to find ways to like optimize this choice and make sure that picking your pivot doesn't take a bunch of time either. Because if picking the right pivot takes too long, it kind of takes away from the fact that this is called quick sort, right? We want it to be fast. So ask yourself, could you pick a better pivot if you knew more about the data set? And what specifically do you think you would need to know? And further to that, how would it affect your choice? So like if you knew it was almost sorted, if you knew it was sorted, if you knew there was lots of duplicates, if you knew there wasn't a lot of duplicates, think about, numbers and different scenarios in which patterns and sequences may arise and try to ask yourself, how would that actually affect your decision in a pivot choice? Because there's some really good exam questions in there to see if you kind of understand why picking a good pivot would make a difference and how you would go about picking said pivot. Okay, anyway, that's all there is to it. Again, feel free to go through the code. I did give it to you. I do care a lot more, though, that you can kind of follow this partitioning algorithm through and understand, the effects of your pivot choice and sort of some of the ways in which the decision of the pivot choice is being made. And then you'll do a lot more work on understanding this and learning about it in future courses. Thanks, everyone, for joining me on this journey, and I hope you have a great rest of your day.